So hi everyone. Now we are going to talk about the chemical crosslinking combined with mass spectrometry with the new algorithm in Misc and MaxLynx. So I'm happy to say that it was part of my Marie Curie individual fellowship postdoc, which I finished last year, last December. So, and this paper was published in January. Whenever I think about the crosslinking and crosslinker, always came to my mind the handcuff. And then we will see why I always remember the handcuffs for crosslinker. Throughout the talk, in the beginning, I will introduce you what is this crosslinking and what about what is the special things about it. And then I will talk about the MaxLynx, what we can do, what can he do for the crosslinking. And then I will introduce you the MaxLynx result from the paper, and then I will end with conclusion. And before I start, I'm curious to know if there's anyone working on crosslinking here. And just out of curiosity, because I was talking out of PTMs and phosphorylation, how many people are working on phosphorylation? Okay, so the crosslinking is getting popular, but it's not as popular as like PTM or some other studies, but it's getting more popular. So let's talk about what is this chemical crosslinking. If you remember yesterday's plenary talk from Dr. Paola Picotti, she was referring the limited proteomics. And then over there, she was also referring that typically the structural information is lost on the normal shotgun, like typical shotgun proteomics experiments. The last 5 days, we actually referred this several times. But so here, let's go quickly what I refer. So basically, in the like simplified version, we have the proteins, and what we do the enzymatic digestion. So we make the smaller pieces from protein, and then because of this, we make such a small pieces, and then we are losing the structure information. So which part of the amino acid they are linked together, or how they are linked. So we are losing this. And when we do LC-MS, we tend to have a spectrum coming from one peptide. Of course, it's possible coming from 2 peptides, co-eluted peptides, but we tend to want to find one peptide, one spectrum for DDA. So I'm referring here for DDA. So DIA for crosslinking in our lab is planned, but not done yet. So now let's talk about the chemical crosslinking. And here I say that chemical crosslinking makes spatially close residues remain together. And then here comes my Lego police officers with the handcuffs, because these crosslinkers are like handcuffs. It goes, and then if there's any close residues within this protein, it will make sure that they remain intact. They remain together. And then I will have these crosslink proteins. And then when I do the enzymatic digestion, unlike the typical proteomics, I will have quite complex sample. So I will have a lot of additional products. And also my spectra will be complicated than the typical shotgun proteomics experiment spectrum. And I also wrote here how we usually refer in the literature about this chemical crosslinking combined with mass spectrometry. And when you read the paper, you will see XLMS, CXMS, or CLMS. So just for you to, getting familiar with the terminology. Okay, so I told you the crosslinkers are like handcuff, but let's have a look how they are special. So we could say that this is a simplified version of the crosslinker, and crosslinker has some special features, special characteristics, and we can divide into the 3 categories. So it could be functionality, could be the length, and could be the MS feature. So in terms of functionality, we could think about the reactive group. What I mean the reactive group is the arms, the ending part. So it might be the homofunctional. Here what I see this crosslinker, both arms are showing blue. I show them blue because they are homofunctional and because they target the same residues on the protein side. It might be heterofunctional, and then here I refer blue and green because one of them targets maybe amine specific, the other one targeting maybe some other type of the residues on your protein. Okay, so we know the type reactive is important to understand our crosslinker. Now we also have the number of reactive groups. We call them bifunctional when they have 2 arms, and it's also possible they might have 3 arms. And when they have 3 arms, the 3rd arm usually for the enrichment when you do the before. And then you cut this 3rd arm, and on MS you always have this crosslinker with 2 arms. We talk about the functionality, now let's talk about the lengths. These 2 reactive groups, they may have some carbon chain between them, so they will be a bit apart. So when they are a bit apart, we call them non-zero. And then here the carbon chain I show it's in orange, but it's also possible then 0. And this is special thing for your experiment. So if you know that your residues on your proteins structure is very close, you want to use a smaller crosslinker, non-zero one, and then so you can target. But if you know that you are aiming on the structure, the residues are quite apart, then non-zero crosslinker won't be useful for you. So then you will go to the, the 0 one won't be useful, so then you need to go to the non-zero then crosslinker to capture the residues on the protein that are a bit apart. And we also have on the MS level, and here what I show, like this is the non-cleavable one, meaning that this crosslinker remain intact on our MS measurement. There won't be any cleavage on my crosslinker. I know that it will remain intact. But for the MS cleavable one, here I have actually 2 sides I show. So what happens on the instrument-wise, in the beginning there was a smaller energy and then the crosslinker is cut. When it's cut, the smaller pieces attach to the crosslinker, and then it will measure a peptide with a partial of a crosslinker. And it's of course possible to have the other part of the crosslinker, and then again you will also have the peptide and crosslinker and measure. These 2 have just different functionalities, different AMR studies. So when you are focusing on the conformational changes, when you're focusing on the smaller protein databases, then we typically do the non-cleavable. But the problem on the computational aspect is that we have, you have to check all the possibilities, and then this can be overcome with MS cleavable because the peptides are smaller and might be, then you can go to protein-wide crossing, protein-wide enrichment. Now let's have a look at the 2 crosslinker example. So on the left, these are 2 popular crosslinkers, and the left one is DSS and the right one is DSS, so DSSO and DSSO. First, let's look at their functionalities. We say that this is homobifunctional. We have 2 arms, and they are same chemistry structure. They have the same structure. And they target the amine reactive groups. And what we know from amine reactive group is that they are mainly targeting the primary amine. And where do we find the primary amine on the protein? We find them on the lysine and protein N-terminus. If we look at the second crosslinker, we see that it is again the same reactive groups there. So the functionality-wise is the same. So it's also targeting the lysine and the protein N-terminus. Now let's look at the length. As I referred, there are these 2 reactive groups, and then we have the carbon chain between them. And on the left one, it's slightly bigger than the right one, and then these are non-zero. And then how we define the length? We define with the angstrom. And then here is 11.4, and this is 10.3. And this information will be useful for you later on the modeling the structure, checking the conformational changes. And the last one, MS Fisher. So as you see on this non-cleavable crosslinker, there is no this carbon chain. There is nothing makes this bond labile to doing the MS measurement. But on the right one, we have the sulfuric acid, and then we know that this makes the structure as very labile during the MS measurement, and then there will be cuts before and after this. Do you have any question? Okay, now we know about the crosslinkers. So we have the crosslinkers, they have different functionality, they have different length, and they have different MS capabilities. Now let's talk about the crosslink products. So typical proteomics experiment, typical shotguns, we have the protein, and we tend to have the single or ordinary or linear peptide we have. But in the crosslinking, we have quite mixed. We don't have only our single, and we actually aim this two peptide crosslink by the crosslinker, because here we retain the information on the structure. But this is not so, it's happening, but we are a bit unlucky to have also the other product in there. We have a lot of single or ordinary peptides. And because they are still the most abundant, there are some enrichment techniques is done for the crosslinking experiment. And we also have this monolink peptide. And here I mean that the peptide has a crosslinker attached, but the other arm of the crosslinker is remain like in the air. And what we really care about mass spectrometry is the mass changes, right? So we know the mass change of this also. Like if it's DSS, it's like 156 Dalton. And there's also the other types, like this is loop link or cyclic or intrapeptide. It's called intrapeptide because the cross-linking happens on the peptide itself. And so this doesn't give as much as information like the two peptide cross-link to each other, but we also have this, and we have the cross-link peptides, interpeptide, and they also called type 2. There are different terminology on the cross-linking in terms of type. That's why I wanted to put it there, but I will refer most as cross-link peptide throughout the talk. And I know also the mass differences for this. I mean, the cross-linking is happened with the known feature. That's why we know the mass shift. But it's also possible that we have some high-order cross-links. What I mean, like this is the combination of different modification. And here we could see that this is like two peptide linked, one cross-linker, and the other one is cyclic. But we don't tend to analyze this. We don't tend to find this on the softwares. And what we usually focus is the peptide, and of course we also put our search this mono and the single and loop link too. Now very briefly talk about the computational tools. So here one schematic version of what happens. So we have two peptides crosslink, and we do MSMS. And this is non-cleavable crosslinker, so it remains intact. And I have peaks coming, fragment ion coming from two peptides. Because I intentionally generate a spectrum containing two peptides, and then I have the mass shift because of peptide. And on top, I also have the other fragments, other type of crosslink products. I need to have specialized algorithm. And this specialized algorithm check this MS data to the crosslinking search database. And here what we see, here are experimental data set, and then here are database, and then these are the available search engines. The search engines have different approaches on the computational aspect. When I started in my postdoc in Jürgen's lab, so there was not so much softwares available doing both but I mean this non-cleavable and MS cleavable. And nowadays we are hearing more and more, and then as I also noticed, crosslinking is getting more popular. So there will be a lot of improvement coming on the crosslinking field. So after we did the searching, we will have the crosslink peptide to spectrum match. So we also refer in the proteomics PSM. This is the peptide to spectrum match. But here, because I have the crosslink peptide, therefore we call this crosslink peptide to spectrum matches, CSM. And later we do the FDR control, and then we have the list of identified crosslinks. So now, like I know on my protein which residues are crosslinks to each other and what I can do with this list. So if I have some structure available, I can check the 3D version. I can go to PyMol, and I can also go maybe the Chimera or some other search, some other program, and then see how the structure and how these crosslink residues are on the structure-wise. So here, it's important that crosslinker impose some distances. And as I referred before, this distance is because of the carbon chain. And then we know this, how much they can expand. And then based on this, we could see on the protein structure how much they are apart, and if it's maybe over exceeding the giving the distance, then maybe there's conformational changes supporting your idea. Or maybe it's within the distance, and then you will say that, ah, yes, so there's no changes on the structure on this side. And it's also possible to do the 2D version. What I mean on this two-dimensional, that you could do some symmetric version, like making circling, and then you could see how this linking is happening between them. For instance, here we have this one protein shown in orange and the other one is in green. And when we have the cross-linking is happening within each other, it's shown as red. But when we have the cross-linking is happening within these two different proteins, it's shown in blue. So it gives me some idea how the communication between these proteins is happening. And this circular is not the only one. You could also do like rectangle shape, or you could also do like a circle and then putting like cross-linking onto each other. Okay, we visualize, we understand how our cross-linking, how our cross-link residues, what are they doing, and what we will in the end, where are we going to use this? So we are going to use it maybe for predicting the structure, or we are also going to use it maybe protein-protein docking. And for protein docking, there is this HADOX, and then they have this X-Links, some tutorial where you could follow, and then you could see how we could use the cross-linking information to able to do protein docking by HADOC. And so this was an example from one study. They find out like which one has the cross-links to each other, and then they predict if there's any conformational changes happen. But the cross-linking is still raw resolution, so it's not very high resolution. That's why it's not used alone, but you use it to complement to other studies, to other techniques, such as the Cairo-EM. We know that Cairo-EM getting more higher resolution, but still it's not like X-ray. X-ray crystallography is not there yet, so it's on the way. But so we could use this cross-linking information to complement with different structural biological techniques. And as yesterday's Paolo Cotti's talk, she also said that they want to use the lipid proteomics and then using some improvement with the other structural proteomics, and she also referred to the cross-linking. So over there, you could also improve the other techniques too. Let's talk about the MaxLynx. So MaxLynx has published in January. So last Christmas, we were doing a lot of reviewing, like lots of replying to the reviews, but it was accepted, so I was happy. It said that there is non-cited, there is no citation, but there's actually some. So one of them is self-citation, but we have 5, so I'm happy. And so on the left, we see the computational workflow. And when we have a close look, we see that we do in the beginning the typical proteomic search, but later we do some cross-linking specific activities over there. And here we do the combining APL. APL files in MaxCon, they are the pick list, and they are sorted by the masses. And this is one of the first process where we combine it. And then we do prepare the search engine, and then where we do the in silico digestion, doing some Andromeda scoring and getting the list. And then we read our crosslink search results, and then we do the FDR control on it. After we finish the FDR control, we write the tables. So at the end of your cross-linking result, you will see that we have another folder, Andromeda 2 folder. And then here you will see the raw identification output for the MaxCon. Andromeda result will be there. And we also have the APLs for the cross-linking over there. And when your cross-linking result is finished, then we will have the new table, crosslink MSMS table, under the TXT folder. So this was the very brief overview what was happening. So in the first step, we are doing 3D or 4D MS1 feature detection. 4D when we do the timsTOF, because we know that MaxCon is able to analyze the timsTOF dataset, but I'm happy to say that you could also analyze the crosslink dataset in the timsTOF by using the MaxLynx. And then we do the pick refinement. And the rest is again the similar. And then we do some cross-linking peptide search because we have different crosslink products. And our spectra are not the same like the typical shotgun proteomics. And then we do some FDR because we also need to do some FDR adjustment on the FDR, on the cross-linking. So let's have a look at the MS1 peak refinement. What we noticed, because the crosslink peptide tend to be bigger, heavier, and that's why the monoisotopic peak detection was not so ideal for some cases. And then here is one example. So we noticed this was the wrong identification when we check also the other competitive algorithm. And instead of choosing 77.83, it was choosing 77.8708. So we expand these gaps, and then you can improve the MS1 peak detection, and then we make some improvement on the identification rate for cross-linking. And later I will show where you can enable this function for cross-linking as well. So MaxLynx is able to do it 2 search modes. One of them is non-cleavable, and here's the representation of it. So what we have non-cleavable cross-linker, and we have the fragment ions coming from maybe only this part, and then they are blue, or maybe only some yellow, and then they are here. But maybe the cross-linking, no, the fragmentation only happened here. So I have this entire crosslink plus 2 peptides, and they are here. So we can do the non-cleavable cross-linker, and we could also do the MS cleavable. So for this MS cleavable, what we know, cross-linker has 2 cut places. When there's the cut happen, then we have 4 signature peaks. On the signature peaks, we have peptides and longer crosslinker, longer part of the crosslinker, and the same peptide, the shorter crosslinker, and it's the same for the blue one. Blue, shorter crosslinker and blue and longer. Because of this, what we know the masses and the chemistry of this crosslinker, we know the delta masses. And this delta mass is very specific for these crosslinkers. And then we can calculate, we can find out who are these peptide orange and peptide blue, and then identify our spectrum. But it's very possible that we don't actually have all these 4 signature peaks. And there's actually some studies showing that they are missing. But they also show that the signature peaks might be, the signature peak tend to be on the top end. What I mean with top end, they are the highest intense peak on my MSMS spectrum. And in this case, I only have 1 signature peak, and this is actually on the most intense peak. And the studies show that the top n equal 3 gives the best results. So that's why we also keep this default value on our algorithm. And we still use the Andromeda scoring function, but we did some changes because of the nature of the crosslinker. So after we do the identification on the peptide to spectrum level, what we do on the MaxCon, we do the FTR calculation. And when we do the FTR, we do the calculate the posterior error probability. For the crosslinking, we changed it, we adapted this to our cases because we don't have 1 peptide, but we have 2 peptides. So which miscleavages are we gonna take? Or are we gonna take the Andromeda score? We adopted this PEP calculation, and I did some tests. It works now, how we do. And another thing is, okay, we do the PEP calculation, but on the FTR level, we have decoys and we have targets. Because we have 2 peptides, they might come from 2 decoys, but it's possible that 1 peptide is target, the other peptide is decoy. So I also take into account, but I say all of them are decoy. And then we did the number of decoy divided by number of targets, and then do our calculation. And I do the FTR calculation for only single peptide, only the monopeptide, and also only the crosslink peptide. So I don't mix these 2 different groups to each other. We don't mix this. Okay, now let's talk about how you could actually configure, how you can run crosslinking on MaxCon. So there is new group-specific parameter, and then here is called crosslinks. And we need to, in the beginning, tell on the mode, what kind of crosslinking is it? Is it non-cleavable or is it MS cleavable? On your experiment, you will know which one is it. And based on this, we will have some different settings. And we hear some defaults. So minimum length, we have it 6. It's a bit less than the typical search because we have 2 peptides. And in total, we will have already 12 minimum peptide length. And then we also have the minimum score. And then, we also have the minimum score, and then we also have some partial score. During the review process, I tested several times how these parameters are affecting the identification result. And these are the best settings that I found. So you don't need to change this parameter, but what you need to change is the crosslinking type and which crosslinker you use. And this is to understand, for you to understand what's happening, but you also don't need to change it. So here we use slightly different terminology to also address the high order crosslinking. And then we say that hydrolyzed monopeptide link is monopeptide because there is only 1 peptide. It's hydrolyzed because it's not linked and some part is missing. Some part, missing is not reacted to the other peptide. And it's possible that this single peptide has crosslinker like cyclic type, and if link within each other, we call them link monopeptides. And what we are interested in is crosslink peptide, and this is the D peptide two peptides, and they are linked to each other. You also don't need to worry about these settings. But if you want to try out to check the higher order, you could play around, of course. And this was for the non-cleavable crosslinker. And this is now about the MS cleavable. For MS cleavable, we change it, say the MS2 cleavable, and we say the DSSO. And then the top N strategy here includes intensity-based strategy. When you enable this, it will additionally check for the top N intensity signature peaks and improve your results. And then you can choose by default 3, but if you want, you could also play with this parameter. Throughout the course, we also show how you can actually configure your identity, how you can configure MaxQuant in terms of modification and proteases. And then we also have some tutorial online to show you. And it's crosslinking section right next to it. It's very similar how we configure actually on the modification side. So you could again either add or duplicate, and then you will write what is the name of the crosslinker and description, and the link composition when your crosslinker has 2 arms and these 2 arms are linked to a peptide. And this is the composition that we give to MaxQuant. And this part, the numeric part, will be calculated automatically after you define it. So you don't need to define, you only need to define this formula. And the hydrolyzed composition is your crosslinker is linked to one peptide, and one arm of the crosslinker is not reacted. And here we give only the formula. Because we have 2 arms on the crosslinker, we can have 2 specificity, 2 different two different reactive groups. And then here we tell them, okay, which residues are they targeting? The first arm. And in my case, specificity is K, the lysine. And where this can happen, it can happen anywhere. Is it possible that protein N-terminus can be also linked? Yes. Sometimes your crosslinker is not aiming protein N-terminus, but C-terminus. In that case, you click on it here. So it might be the specificity 1 section and the 2, they are equivalent, but not always the case. And when you have MS cleavable, you enable this click here, and you need to tell the software what is this long and short part of the crosslinkers fragment pieces. Again, what you need to define, only the formula. After you define the formula, we will calculate the numeric value. So another tips, like where do we see this also, the configuration files? So they are under the configuration folder. And then here you will see the crosslinks XML. You could also go and check how the other crosslinkers are identified. How you can enable the peak refinement, the one that I was referring in the beginning, you need to go to the miscellaneous tab on the group specific parameters, and then here is the refine peak. So this is by default is not selected because it's more optimized for the crosslinking studies. So if you study crosslinking, please enable this function. And another important aspect to change from default settings for the crosslinking, even though we said, I'm just now saying because you don't change the settings. We ask you to keep the default settings as much as possible unless you know what you are going. So this is one of the examples. So you need to improve the maximum number of Misc cleavages because like in this lysine is our trypsin. If you are using trypsin, so the lysine will be crossing also because of DSS, some other amine reactive groups. So you need to actually increase your Misc cleavages to able to find the crosslink peptide. So please change also instead of 2 to 3 the maximum Misc cleavages. And here the peptide length and the peptide mass. The maximum peptide mass is 4,600, but please also increase this for the crosslinking because crosslink peptides tend to be heavier, so it shouldn't be the same like the typical proteomics experiment. Another things about the timsTOF. On the timsTOF, on the maximum charge, we say it's 4, but for the crosslinking, to enable to see this heavier peptide on the instrument, they tend to have higher charge. And because also they have 2 lysine in the end with the typical crosslinker and the lysine of the trypsin, we have the higher charge states typically for crosslink peptide. So it is not, so you will probably miss something if you don't change your timsTOF maximum charge setting from 4 to 6. So you please also change this one. So in the end, what will happen? You will get the TXT file, and it is crosslink MSMS TXT, and then this is how it will look. So you will have a lot of new columns for you if you are the first-time user. And to understand how these columns are, there is this tables PDF, and then here I wrote what are these columns are referring. We analyze the sample, we have our identification, and we do the visualization of the MSMS2 label. And then this is like a new feature also on the visualization for crosslinking. So what you will do, you will go to identification tab here, and then there will be the crosslinks MSMS, and then you can sort based on score or PEP. And then when you click, and when you also click the display spectrum, you will see this kind of visualization on your MaxQuant result. So here we have the peptides, the MSMS spectrum is annotated based on your fragmentation. And then here we have 2 peptides, the longer peptide and shorter peptides. And if you see that on the longer peptide, Y ions are shown as red. And then here you could find them too. They are also shown as red. And then here we say Y1, and then I don't use any other annotation. But here, just to be sure, I put Y1, it's somewhere here. And then I say that alpha. So here, all of the Y, if it comes from the longer peptide, they have annotation of alpha. Because in the literature, we say it, the longer peptides that are crosslinks are annotated as alpha, and the shorter part of the peptide is beta. And it's the same for the blue one. The blue one, and here is blue is B, and then B is alpha, the longer peptide. And the purple one, here we show the Y ion in purple and the beta. And then lighter red is shown B fragment ion and beta. Let's talk about the MaxLynx original results. So the first is about the published synthetic peptide dataset. So this was published 2 years ago. So they had some synthetic peptides and they put them into 12 groups. 5 minutes. Okay. Okay. Okay, so we put them into 12 groups, and then we only, every individual groups, we make the cross-linking. So in the end, for every groups, we know that the cross-linking here, for instance, happens only within the blue, here only within the orange, here only within the green. And later, they put all of them together and introduce the mass spectrometer. And then they say that these are my possible combination. What I mean again, only the orange ones and only the blue ones only green and so. And some of them will be impossible because we didn't put them next to each other. Like, I don't expect to see the green linked together with the orange or green together with blue. And based on this, we could actually see how the crosslink search engines are able to find the true hits and false hits. So that's what we did. So I used already their results, Peeling, Stavrox, and ical. These are some other popular search engines. And OpenPepXL was the recently published search engine. And here we have the crosslink to spectrum meshes, and here is the number of crosslinks. So the upper part shows the non-cleavable crosslinker, and the lower part shows the MS-MS cleavable. And what we see here, the correct ones only comes from here within the groups where I find the correct. And then we can see that MaxLynx is performing very well on the 1% of FDR compared to the other search engines. And in terms of correct, and of course, we also find some incorrect ones. And at the moment, we have the FDR control on the PSM. I don't think that so many search engine has the FDR control on the crosslinks. And when we go from this CSM to the crosslinks, we have some more incorrect ones because we know that the FDR is actually higher than 1%, but still we are finding relatively here on this set the best. And then on the non-MS cleavable, we were also doing good. So I will quickly go through what I want to show. Maybe like the timsTOF, we also analyzed it on timsTOF. For this, we did BSA, and then we did the MS cleavable. And then we just check how many of the spectra I am finding and how many of them incorrect. And my FDR on this CSM level was again below 1% FDR. And another one we tested on a large scale proteomics because the advantage of using the MS cleavable to able to do the proteome wide. For the non-cleavable crosslinker, we could only do maybe 10 or maybe 50 proteins. And we tend to have a smaller number of proteins on your FASTA file. But when you do MS-MS cleavable, you could actually use the whole proteome. So here we show that MaxLynx is also capable of doing the MS cleavable cross-linking search. And then another paper like this, I'm happy, like this was recently published. So here, this was an independent study. So we were not involved, and then they tested different search engine and different crosslinkers that I also didn't test it. So for instance, here there's a crosslinker called ADH, and then these are the different softwares. And then what I could see, MaxLynx is doing well for this crosslinking. Maybe it's not doing the best, but relatively good compared to the others. And this is another crosslinker. I actually didn't test it, so I was not so sure how it will be, but I'm so happy that they did the test. Thank you very much. And then, so here we could see the MaxLynx is also doing very well for this crosslinker. And they also tested for some other cases, like here they intensively test for different way of calculating FDR. And over there, MaxLynx was also doing very good. So as you know that we also give the Perseus plugin, and then last year there was a exchange student from US, so he was working with us for a few months, and then he helped us also do some plugin on the Perseus, so you could actually use the PyMol, you can give the input of the crosslinking to there. What I want to say here that you could also contribute now to the crosslinking our workflow by making our own pipeline plugin. And then what I also want to say that every year there's this Max Planck summer internship is happening. So if you know someone, they could also apply here. And with this conclusion, I want to say that crosslinking is getting popular, but it's not as popular as the phosphorylation as we see here on the room. And MaxLynx is a new crosslink peptide search engine, and it enables for you to find non-cleavable and MS cleavable. And it's freely available. I tested it on Windows and Linux, and it works on both cases without any problem. And we want to actually do more things on the MaxLynx to improve the, to extend our portfolio, like doing the second peptide shares and DIA, also on doing MS3 crosslink. And then I hear say that I plan to submit manuscript. This was last year, but everything is awesome, so we publish it. So I am happy to say that this guy, the crosslinker, I'm hoping that he will find make sure the structure on this will be together. With this, I want to thank you. And I also want to thank the European Marie Curie Individual Fellowship for this supporting me. Thank you.